So for our first problem, it just says expand 1 minus sine squared x raised to the 5th power. Well, doing this the old-fashioned way, we would have to write 1 minus sine squared x out 5 times, and then proceed to multiply those 5 binomials by each other. That's going to take a really long time, because a binomial times a binomial is going to give you a trinomial, and then a trinomial times a binomial is going to be 4 terms. 4 terms times a binomial is going to be 5 terms, and so forth. And we would have to do that until we had multiplied through all of those things. Well, turns out that there is a better way to do this, and it's called the Binomial Theorem. As we see above, it says to raise a plus b to the nth power, we have a nice formula. We've written it out in the long notation, but then it can also be written in sigma notation as the sum as I goes from 0 to n of n choose I, a to the n minus I times b to the I, where n is our exponent. So we may or may not remember what the choose function is. So if we have something that looks like this, p choose r, or c choose r rather, when you really use anything. So c choose r is equal to c factorial over r factorial all over c minus r factorial. So basically, for instance, if we wanted to calculate 5 choose 2, that would be 5 factorial all over 2 factorial, and then we would have 5 minus 2 factorial. So that would give us 5 factorial over 2 factorial times 3 factorial. And then we'd have to expand that out. And what is it that the factorial function represents again? Well, it tells us to multiply, starting at that number, all of the positive integers, positive whole numbers together, descending down. So 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 3 factorial is 3 times 2 times 1. And then we would have to simplify and see what we get. So we'll notice when we do this, some of these things just cancel out very nicely. So the 1's reduce out, the 2's reduce out, the 3's reduce out. And that leaves us with 5 times 4 over 2 times 1. So 20 over 2 reduces to 10. So 5 choose 2 is equal to 10. It's worth noting our calculator knows how to make these tables, or knows how to do these. So if we wanted to do, say, 5 choose 2, we're going to press 5 on our calculator. We then press math, and we go all the way over to probability here. And they do NCR is their notation. So 5 choose 2. And it agrees with us that it's equal to 10, right? So in general, we can do any of these calculations that we need on our calculator. If you have to do a whole bunch of them, like what we're seeing here, I find it easier to put them into, say, y equals, and then you would go, we're going to do 5, and then we go math, we go over to here, we're going to go 5 choose, but instead of putting a number in, go 5 choose x, and then go second table. And if we go to 5 choose 0, it's going to be equal to 1. 5 choose 1 is 5. 5 choose 2, the one we just found out, is 10. 5 choose 3. That way you don't have to type them all in manually. You can just put it in with the appropriate top number in your calculator and then generate all of the coefficients that we're going to need. And we're actually going to use this table, as we'll see, in this problem. It will be helpful in what we're trying to do. So back to our regularly scheduled problem here. So we want to calculate 1 minus sine squared x to the 5th power. Well, according to our formula, what we're going to get is something that looks like this. So we're going to have that this is equal to the sum as I goes from 0 to 5 of 5 choose I, and then we're going to have our A in our formula. It's going to be 1, and our B is going to be negative sine squared x. So then that's going to give us A, or in this case 1 raised to the 5 minus I, which is not going to be anything, times B, which is going to be negative sine squared x, just raised to the I. So now, if we wrote all of that out, which I will this time, it would be 5 choose 0, because we let I go from 0 to 5. Well, 1 to any power is just going to be 1. So we're then going to have our B raised to the 0. We'll write it out. Negative sine squared x to the 0 plus 5 choose 1, and then we're going to have our negative sine squared x to the first plus 5 choose 2, our negative sine squared x squared plus 5 choose 3, negative sine squared x to the third plus 5 choose 4, negative sine squared x to the fourth plus 5 choose 5, negative sine squared x to the fifth. So now we need to resolve each of these things, right? So we know from our calculator, if we go to 5 choose 0, what is that going to equal? 1. So we get 1, and then anything raised to the 0 power is also 1, so we get 1. And then we have 5 choose 1 is going to be 5. If we look at our calculator. So 5 choose 1 is 5. And then we have negative sine squared of x raised to the first power. So this is negative sine squared x plus 5 choose 2. When we look at our calculator, 5 choose 2 is 10. So 10 times negative sine squared squared is going to be a negative times a negative is a positive. We're going to get sine to the fourth x plus 5 choose 3 is 10. And then negative sine squared times negative sine squared times negative sine squared is going to be a negative sine to the sixth x plus 5 choose 4 is also 5. And negative sine squared to the fourth is going to be a positive sine to the eighth x. 5 choose 5 is 1. And negative sine squared to the fifth is going to be negative sine to the 10th x. So then finally we get 1 minus 5 sine squared x plus 10 sine to the fourth x minus 10 sine to the sixth x plus 5 sine to the eighth x minus sine to the 10th x. And that's what you get if you raise 1 minus sine squared x to the fifth power. So the binomial theorem gives us a way to raise binomials to very large powers by computing each of these things. So we'll have occasion to use this to calculate some things in this section. All right.
May I ask how you got the plus 10?
All right, so to integrate sine to the fourth power x dx, we are going to have to use one of our trigonometric identities. So for this first one, we're going to need to use the half angle identity right here. So we want to use this identity, and this identity works on sine squared. So if I have sine to the fourth power, how can I write it as sine squared? Well, we want to use the following property, that if I have a raised to the fourth power, this is the same as a squared squared. Because if I have a power of a power, it's the same as multiplying the exponents together. And since I want a sine squared, what I really want is sine squared of x raised to what power is going to give me sine to the fourth. So sine squared squared is the same as sine to the fourth. So using that, we have the integral of sine to the fourth of x dx is the same as the integral of sine squared x squared dx. And now we can use this identity on sine squared. So then this is the same as the integral of 1/2 times 1 minus the cosine of 2x squared dx. So 1/2 squared, because we have our factors, is just going to be 1/4. But then I'm going to have 1 minus the cosine of 2x squared dx. And I do need to FOIL this out. So pulling my 1/4 out in front of my integral, I need to multiply out the binomial 1 minus the cosine of 2x. So a minus b squared is going to be equal to a squared minus 2ab plus b squared, right? So we're going to get 1 minus 2 cosine 2x plus cosine squared 2x dx. So we need to integrate this, but before we can, we still can't integrate cosine squared. We're going to have to use the half angle identity again. So when we do that, we get 1/4 times the integral of 1 minus 2 cosine 2x plus, and then the half angle identity for cosine, if we go back up here, our half angle identity for cosine is exactly the same, but instead of minus, it has a plus. So we end up with the following. We use our half angle identity on this, which gives us this. So we end up with 1/2 times 1 plus, but we already have a 2x. So if we double the 2x, we get cosine 4x dx. So now, after all this, we're finally ready to take our integral. Collect a few like terms. So we have 1 minus, let's distribute first. So 1/2 times 1 gives us 1/2 plus 1/2 the cosine of 4x. So then 1 plus a half gives us 3 halves minus 2 cosine 2x plus 1 half the cosine of 4x dx. So we do our integral. We have 1/4 times everything. The antiderivative of 3 halves is 3 over 2x. The antiderivative of cosine 2x, the antiderivative of cosine is sine, but then we have to divide by 2, because it's not x, it's 2x, plus 1 half, and then the antiderivative of cosine is going to be sine once again, but it's cosine 4x, so we have to divide by 4 plus our arbitrary constant. So a couple of things reduce out. Some of these multiply together. So 1/4 times 3 over 2 gives us 3/8 x minus 1/4 times sine 2x is sine 2x over 4. 1/4 times 2 times 4, so 4 times 2 times 4 is 32. So plus the sine of 4x over 32 plus c. And that's going to be our antiderivative of sine to the 4th power of x. So a couple of comments. When we are doing trigonometric integrals, there are going to be tons of ways to do them. I'm going to show you the canonical way using sum identities. There are millions of trig identities out there. If you use different trig identities, you can still do these integrals. Your answer will look different depending on which trig identities you used, but they will be equal if you check them at every point. So with trig functions, even though they don't look the same, they might be equal, right? Because with trigonometric identities, we can change many things into many other things. So just be aware that trig integrals may look very, very different in their final form answer, but as long as it is an antiderivative, it's correct. So you might get a different looking answer than someone else, and that's okay. That's normal. It's going to happen, and I guarantee you if you type some of these into Maple to check them, I'm not even sure where Maple gets its answers sometimes. They're not wrong, it's just not what a human would get. So computers do interesting things when it comes to solving these things. Same thing if you type it into Wolfram Alpha or something else on the interwebs. They'll give you antiderivatives, and they might be the same as yours. If you're ever worried and you're using one of those programs, subtract the two answers and simplify. If you get 0, then they're equivalent, right? So that's a good way to check that two trigonometric expressions are equal really quickly, is just subtract them, and if they are equal, you'll get 0 for every value that you put in. So keep that in mind, that there are many ways to do these. Okay, let's take a look at our next example. Which is for you guys. Let's go ahead and have you try number 1. And do this. So if we use our identity, the cosine squared of x is going to be 1/2 times 1 plus the cosine of 2x dx. So pulling our 1/2 out in front, we really just need to integrate 1 plus the cosine of 2x dx. That gives us 1/2 times the antiderivative of x, or of 1 is x. The antiderivative of cosine is going to be sine 2x over 2 plus c. So we distribute in, and we get 1/2 x plus sine 2x over 4 plus a constant. So in each of these last two integrals that we did, you may have noticed we started out with an even exponent on only sine or an even exponent on only cosine. It turns out that that is a pattern. The strategy for integrating even powers of sine or cosine requires us to use the half-angle identity. And we may need to use the identity multiple times, like what happened in the example that I did earlier. Sometimes with those powers, you may need to combine them with the binomial theorem, right? Because if we go back and look at what happened in example 1, expanding 1 minus sine squared to the 5th, this would be cosine to the 10th power is what that's equivalent to. This isn't a good strategy for integrating that, but we'll see that sometimes we will end up with giant binomials that need to be raised to powers. Kind of like what happened in example 2, this time we only had to do it to a square, but if that would have been sine to the 6th, we would have had to cube something. If that would have been sine to the 10th, we'd have had to raise something to the 5th power. So that's why we want to have that binomial theorem hanging out, because you really don't want to multiply 5 binomials by themselves. You've got better things to do with your time. All right. So now we want to switch to a new type of trigonometric integral. So this time we are going to have sine and cosine, and the other function, sine or cosine, may or may not be present. But if one of them has an odd power, it turns out that the integrals are actually a little bit easier. So if you have an odd power of sine in it or an odd power of cosine, that is the wrong thing that I put there. We need this one. Apparently I did not copy it to the clipboard. So when we have odd powers of sine or cosine, our strategy is going to be the following. So as mentioned, it doesn't matter if sine and cosine are also present. All that matters is that sine is odd or cosine is odd. If one of them has an odd power, our strategy is to rewrite that odd number as raised to the m minus 1 power times itself, because then if you add those two things together, you would get m when you added their exponents. So you're going to rewrite your odd exponent as an even exponent times something with an exponent of 1. And then we are going to make a u substitution on the thing that now has an even exponent, because the one term that we peeled off will become our du. This will make more sense when we see an example right now. But that's our strategy when the exponents are odd. So let's take a look at example number 3. So it fits the pattern we're looking for, as the exponent on cosine this time is 9, and 9 is an odd number. So the first thing we do is we're going to rewrite this as the integral of cosine to the 8th of x times cosine x dx. We are then going to focus on this piece right here, and we need to rewrite it as sines using the Pythagorean identity. So the Pythagorean identity that we're going to be using in this case is this guy right here. So sine squared plus cosine squared is equal to 1. So we're going to rewrite this first as sine squared of x raised to the 4th, and then solving this identity for sine squared, or for cosine squared, we get that cosine squared of x is equal to 1 minus sine squared x. And we are going to take and substitute this guy in, and we end up with the integral of 1 minus sine squared x to the 4th power times cosine x dx. So first thing we did was we rewrote it as this. As these two. We then used our Pythagorean identity right here to rewrite this as the other trigonometric function. So we rewrote our cosines as sines. And then finally, we make a u substitution using the very last f right here. So we're then going to use this as our u. So if we let u equal to cosine x, then du is going to be negative sine x dx. And we solve for dx by dividing by negative sine, by dividing by negative sine. And we end up with dx is equal to I did that backwards. I substituted the wrong thing because that thing's du. Sorry. We're supposed to let u equal to our sine, which was what we substituted out. So then du is going to be cosine x dx, which is exactly what we have left. So then we substitute all of this into our integral, and we get 1 minus u squared to the 4th times du. And this is what we're going to have to integrate. So now we're going to have occasion once again to use our binomial theorem, because what do we need to expand? 1 minus u squared to the 4th power. So in our binomial theorem, this guy is going to be the sum as I goes from 0 to 4 of 4 choose I times 1 to the 4 minus I times negative u squared to the I. So once again, if we generate our table on our calculator, we go to our y equals, and this time we want 4. So I don't want the graph, I want the table. Scroll back up. So we're going to have our coefficients are 1, 4, 6, 4, 1. And 1 to any power is going to be 1 again, so it's going to be 1 plus, or actually minus, because it's got a negative sign. So our next one is going to be minus 4 u squared plus our next one, 4 choose 2, is going to give us 6 u to the 4th minus 4, and we're going to go back to 1, 4 u to the 6th, and then 1 times u to the 8th. And that is going to be our expansion using the binomial theorem. So now we need to integrate u to the 8th minus 4u to the 6th plus 6u to the 4th minus 4u squared plus 1 du. So we get u to the 9th over 9 minus 4u to the 7th over 7 plus 6u to the 5th over 5 minus 4u cubed over 3 plus u plus our constant c. But then what was our u when all of this started? Sine x, right? So we get sine to the 9th x over 9 minus 4/7 sine to the 7 x plus 6/5 sine to the 5th of x minus 4/3 sine cubed x plus sine x plus c. And as you can imagine, if you wanted to try to use some trigonometric identities on that, you could turn it into 10,000 other things, right? So you could factor out a sine, then you'd have a bunch of even powers of sine, turn those into cosines. You can get all sorts of crazy answers that will be equivalent to what you're looking at. All right. So the first thing we're going to do is write it as sine squared x times sine x dx. And then we are going to rewrite this as cosines. So we use our Pythagorean identity, and we get sine squared is 1 minus cosine squared x times sine x dx. And we're going to let u equal cosine x, then du is negative sine x dx. Divide by negative sine x, divide by negative sine x, and we end up with dx being negative du over sine x. So substituting all of that into our integral, we end up with 1 minus u squared times sine x, and then our dx becomes negative du over sine x. And as should happen, our signs reduce out, and negative du times 1 minus u squared is the same as u squared minus 1 du. So our antiderivative is u cubed over 3 minus u plus c, and our u is cosine, so it's cosine cubed x over 3 minus cosine x plus constant. So that would be our antiderivative. All right, so let's do a couple more examples. So our next one involves a mixture. So the strategy for evaluating products of sine and cosine depends on the exponents on sine and cosine. So there are three cases. M is odd, n is odd, or neither m nor n is odd. Those are the only cases we care about. So basically, either the three distinctions we want to make is one of them is odd or neither of them is odd. If they're both odd, it turns out there's going to be more than one way to do it, and you'll get the same correct answer in the end, as we said. So, but all of these actually reduce back to the cases that we've been talking about already. So case one, m is odd. So when we have sine cubed x times cosine squared x, we're going to use the same strategy as if there is only sine or cosine. So in this case, we have sine as odd. So what was our strategy? We're going to rewrite, I'm going to put the cosine first because we're not going to use it. And then I'm going to rewrite sine cubed as sine squared x times sine x dx. And then we rewrite these as cosines. So that's going to become 1 minus cosine squared x. So we get the integral of cosine squared x times 1 minus cosine squared x times sine x dx. And then after we did that, just like in the previous u try, what do? We let u equal to cosine. So if we have u equals cosine dx, then du equals negative sine x dx. So solving for dx, we get dx is equal to negative du over sine x. And we substitute in. So we get u squared times 1 minus u squared times our sine x, and then our dx is negative du over sine x. And once again, all of our x's reduce out as they should, and we have a new integral in u only, which we can then integrate. So once again, I'm going to distribute that minus sign into 1 minus u squared to make it u squared times u squared minus 1 du. So that's the integral of u to the fourth minus u squared du. And now it's just a polynomial. So we love that antiderivative. It's u to the fifth over 5 minus u cubed over 3 plus c. And we end up with cosine to the fifth x over 5 minus cosine cubed x over 3 plus a constant. So odd powers make integrals easy when it comes to trigonometric integrals. The ones you're going to discover that are a pain is when all of the exponents are even. You essentially end up having to use that double angle identity like 1,000 times if the exponent's big enough. As we've seen, they just kind of chain into these big, long, ugly things. All right. It is your turn. Let's go ahead and resolve this. So the first thing we're going to do is rewrite our cosine in terms of sines. So cosine cubed, same as cosine squared x times cosine x. That gives us sine to the sixth x times cosine squared x times cosine x dx. And we rewrite that as 1 minus sine squared x, giving us the integral of sine to the sixth x times 1 minus sine squared x cosine x dx. And we let our u equal sine, and then we let du be negative, or du is going to be positive cosine x dx, or du over cosine x equals dx. Substituting all of this in, we get u to the sixth times 1 minus u squared times cosine x, and we get du over cosine. Those guys reduce out. So finally, we end up with u to the sixth minus u to the eighth du. So we get u to the 7th over 7 minus u to the 9th over 9 plus c. So that gives us sine to the 7th x over 7 minus sine to the 9th x over 9 plus our arbitrary constant, right? Okay, so hopefully we're starting to notice a pattern here with these, right? So let's take a look at the one that's different. So case 3, where they're both even. And as I alluded to earlier, this is the not fun case. When they're both even, this is when it's ugly. So we want to integrate sine and cosine. So our strategy is we convert to all sines. Or convert to all cosines. And either way will get you the same correct answer. In this case, since cosine has the smaller exponent, it may be easier to convert it into sines, because cosine squared of x is going to be 1 minus sine squared x. So then that would give us the integral sine to the 4th x times 1 minus sine squared x dx. Distributing, we would get sine to the 4th x minus sine to the 6th x dx. So then from here, this is the same as example number 2, right? Even powers of sine or cosine is double angle identities for forever, essentially. So we use double angle identities to help simplify it. We'll note that this is exactly example 2. And this one, or for both of them, we would now use double angle identities. So sine to the 6th of x is sine squared x cubed. And then by the double angle identity, that would be 1/2 times 1 minus the cosine of 2x cubed, because that's our double angle identity. So that would be 1/8 times 1 minus the cosine of 2x cubed. And then here, we're going to need to use the binomial theorem. So we would get 1/8 times 1 minus 3 cosine 2x plus 3 cosine squared 2x minus cosine 2x cubed. So now that we've got this, it just keeps getting even messier, because now I have another even power of cosine, right? So what would I have to do with this? Again, right? And we're off to the races. Odd power we could do a u substitution on, and the rest of them we could integrate, right? So for our double angle identity on this piece again, we would have 3 times 1/2 times, this time it's going to be positive 1 plus the cosine of 4x. And then finally we could distribute all of that through and do our integrals. So I'm going to leave this here if you wish to finish, because we can integrate all of those pieces. Because there's some other examples we need to do. But as the powers get larger, it just basically becomes rinse and repeat. So if you ever start seeing powers more than like 6, as we saw, they get really messy, right? So that's why we have computers. But in theory, we know how to do these, right? It's just the same process, turn the crank, rinse and repeat, until everything's down to nice manageable powers using that identity as many times as you need to, frankly. Okay, so now there's a couple more integrals that we are going to need. So with these ones, I will show you why they work. They are both U substitutions, but in practice, they are easier to just memorize, because especially the second one, when we see it, unless you know what the answer is, you would never pick the U. It's mathemagics. They pulled a rabbit out of the hat with the second one. So most likely what happened is somebody took the derivative of the right side and said, oh, it simplifies to this. So since derivatives and integrals are inverses, we know this has to be the integral of this. And then we came up with a procedure to justify it. So this is not uncommon in math when you know what something's supposed to be. If you know what the answer is, it's a lot easier to find a path to get there, because the answer often gives you clues. So let's talk about the first one. We want to do the integral of tan x dx. So our integral, our strategy for that is to write tangent as sine x over cosine x dx. And then we're going to let u equal cosine x. So then du is negative sine x dx. So then dx is negative du over sine. And if we put all of that into our integral, we get sine x over u times negative du over sine x. Our signs reduce out, and we are left with the integral of negative du over u. Well, 1 over u du is the natural logarithm, so that's the negative natural log of the absolute value of u plus c. Pulling our minus sign in as an exponent gives us the natural logarithm of the absolute value of u to the negative 1 plus c. Which is then the same as the natural logarithm of 1 over u plus c. So then we have the natural logarithm. U is cosine. So that's 1 over cosine x plus c. But then by the reciprocal identity, 1 over cosine is equal to secant. So we get the natural logarithm of the absolute value of the secant of x plus c. So that one's a pretty straightforward U substitution. The integral of secant, not so much, but let's go ahead and do it. The answer is supposed to be the natural logarithm of secant x plus tangent x plus c. So we want to integrate the secant of x dx. So this is where I said the mathemagic comes in. We're going to pick u to be secant x plus tangent x, because why not? Well, the real answer is because it works. So now we're going to calculate du. So du is the derivative of secant is secant tangent, and the derivative of tangent is secant squared x dx. So then we solve for dx, and we get dx is equal to du. And we have a common factor of secant there, so I'm going to factor that out. Secant x, and then that leaves a secant x plus tangent x. And secant x plus tangent x, oh, well, that's u, right? So then this is equal to du over u times secant x. Okay. So now we substitute all of that back into our integral, and we have secant x times dx, which is du over u times secant x. Our secants reduce out, and we're left finally with the integral, once again, of 1 over u du, which is the natural logarithm of the absolute value of u plus c. And u is that miracle that we picked way back in the beginning because it works. So this is what I was talking about when I said, unless you know what the answer is, you would never pick the u. So this one is, for all intents and purposes, just memorize it. Because otherwise you have to, because that's how you would do the u substitution to get it. So unless you know what it is, you're never going to guess the right u, because it's not even in the problem. Right? So they literally pulled that one out of their hat and said, ta-da, we're done. All right. So turns out when we are doing these types of integrals, and when I say these types, I mean sines versus cosines, compared to tangents versus secants, they are actually, the identities, really the same thing. So there are two ways that we can resolve this integral. So the strategy for evaluating integrals of the form tan n secant n has two cases. Case 1, n is even. We rewrite secant as secant squared times secant of n minus 2x, and then use the Pythagorean identity to rewrite the secant of n minus 2 as powers of tangent. And then we substitute u equals tangent, because then du, the derivative of tangent, is secant squared. And we've preserved a power of secant squared to substitute out. Case 2, if m is odd, we rewrite tangent as tangent of m minus 1 times tangent, and we save a factor of tangent x secant x and use the Pythagorean theorem to rewrite tangent m minus 1 as powers of secant and substitute u equals secant, and we get the same thing happening. It's worth noting in these, if you're willing to do a little bit of algebra or a lot of algebra, secant and tangent are both sines and cosines. So note an alternate method is to rewrite this as the integral of sine x over cosine x, and secant is 1 over cosine, so 1 over cosine to the 4th x dx. So then that's sine x all over cosine to the 5th x dx. And let u equal cosine, and then du is sine. And you'll be integrating 1 over u to the 5th. But that won't always work, but it's a nice trick to have in your pocket, because that integral is a lot easier than the one we're going to do right now. But we have to have the full generality of this, because that method, depending on the powers, won't always work. But it's a great one when it does, because it will save you tons of time. But to be thorough, we must do this in its generality. So in this case, we have tangent to the first, secant to the 4th. So we are going to use, in fact, either of the cases we mentioned will work in this case. So let's rewrite this thing as the integral of tangent x secant squared x dx. Secant squared x is 1 plus tangent squared x. So we would get tan x times 1 plus tangent squared x times secant squared x dx. And we let u equal to tangent, and du would be secant squared x dx. So that means secant squared x dx is the same as du. So our integral then becomes u times 1 plus u squared So that gives us u plus u cubed du, which is u squared over 2 plus u to the 4th over 4 plus c. So then that gives us tan squared x over 2 plus tan to the 4th x over 4 plus c. So that one wasn't bad, but the first method's definitely faster, right? And by the way, your answers would look nothing alike, but they are mathematically equivalent. All right, I actually just stole 1 minute of your life. My apologies. So to integrate this, the first thing we're going to do is rewrite tangent as tangent squared x times tangent x secant x dx. We're then going to make use our Pythagorean identity on this and rewrite tangent squared of x as tangent squared x plus 1 equals secant squared. So this is going to be equal to secant squared x take away 1. So that gives us the integral of secant squared x minus 1 times tan x secant x dx. And we're going to make our u substitution, u equals secant x, then du is going to equal secant x tangent x dx. So this gives us the direct substitution. If we have secant x tangent x dx, that's the same as this piece right here, and we substitute in our u, we're going to end up with the integral of u squared minus 1 du, which we can then integrate as u cubed over 3 minus u plus c, which gives us secant cubed x over 3 minus secant x plus an arbitrary constant, right? So with these trigonometric integrals, really the most important part is being able to identify which method we're supposed to use, right? And once we have that, the integration usually falls out pretty quickly. So it's really all about knowing which procedure to use for each particular integral. All right. So the next one we want to talk about is integrals of the type where we have mixtures of sines and cosines where the arguments are not equal. So for the most part, most of our trig identities preserve the argument of the trig function or relate them to either double or half their amount. So if they're just completely different, the strategy is to use the product to sum identities in order to simplify these. So anytime we have a product of these like this, we're going to have to use one of our identities. So if we go back to the very first page, we have our product to sum identities. Right here, and there are 3 different ones for us to look at. And in this case, we have a product of sine and cosine. So that's going to suggest that we use that identity. So we have sine 3x times cosine 5x, right? So in this case, we're going to note that our a value is going to be 3x and our b value is going to be 5x. So we get by our identity that this integral is then equal to the integral of 1/2 times the sine of a minus b, so that's going to be 3x take away 5x plus the sine of a plus b, which is going to be 3x plus 5x, all dx. So we pull our 1/2 out of our integral. And we simplify. We're going to have the sine 3x take away 5x is negative 2x, plus 3x plus 5x is 8x. And if we want, there's a couple more things we can do. Sine is an odd function, so that means we can take the negative outside of the sine function. If it was cosine, remember cosine's an even function, so it would have stayed the same, just without the minus sign. And now we can just do each of these integrals by themselves. So we get 1/2, and the antiderivative of sine is negative cosine, but we already have a negative, so that's going to make it positive. So we get cosine 2x, and we divide that by 2. Plus, we now have our 1/2. We're going to do this one. The antiderivative of sine is still negative cosine. So cosine 8x, but we have to divide by 8, plus an arbitrary constant. So cleaning up our algebra, we end up with the cosine of 2x over 4, distributing the 1/2 in, the cosine of 8x all over 16, plus an arbitrary constant. All right, so